Hi guys, thank you so much for joining me. In today's lesson, we are looking at grade 11 probability and we're consolidating all of the questions that you have been practicing so far. We're going to look at some of the questions where you've had more problems than in other questions. Okay, so we're going to start with question 1, and this one is based on a Venn diagram. Often learners get questions with Venn diagrams in an exam and they're not quite sure where to start. So hopefully by going through this question, you'll have a better idea of where you need to start when you are asked to draw the Venn diagram for yourself. All right. So in question 1, we are told that 350 people were asked about the sport that they enjoy watching the most. That 350 is important because it tells us the total number of elements in the sample space. Okay? It was found that, and I'm not going to read through all of it, but basically it tells you how many watch soccer, how many watch cricket, and how many people watch rugby. You will see that soccer is represented by the symbol S, cricket is represented by C, and rugby is denoted by an R. So generally when we look at Venn diagrams, in this case the question says draw a Venn diagram to illustrate your results and hence find X. We see that X is the number of people that watch soccer and cricket but not rugby. So generally when you draw a Venn diagram where there are multiple events happening at the same time, it is always a very good idea to start with your intersections first. So in this case, because we are dealing with three different things, there are people watching soccer, there are people watching cricket, and there are people watching rugby. So there must be a point where all three events intersect if these events are not all mutually exclusive. So we will look for a point where all three events intersect, and that is where we start. So in this case, we see that 78 people watch all three. So we start by making three little circles. We're going to say one represents soccer, one represents cricket, and the other one represents rugby. And then we start with the intersection of all three. Once you've got the intersection of all three, you then move on to the intersection of each of the two sports that people watch. So for example, you'll see that 53 watch cricket and rugby, but not soccer. So next we will fill that in. Then on the Venn diagram, we will fill in the number of people that watch soccer and rugby, but not cricket. And then X, which is watch soccer and cricket, but not rugby. And I'm going to show you now because I have drawn this up quite nicely. So we'll see that we fill those in after we fill in the intersection of all three. Importantly as well, they say that 38 people do not watch any of the three sports. So if you think about this is your Venn diagram, and then there's a rectangle around the three circles showing your total sample space. Well then, the number of people that do not watch any of the three sports is the number of people that fall out of these three circles. So they will be the people that are outside of those three circles in your sample space. Okay, so we start with the sample space, as I said, showing your three circles. We're going to have soccer, I think it was cricket, and rugby. And where we start is where all three of these circles intersect each other. And they said that 78 people watch all three sports. So that's what I'm going to fill in, where the three circles. You see, there's only one point where all three circles are intersecting, and it's just where I've put the 78. They then tell you that 53 watch cricket and rugby, but not soccer. So 53 watch cricket and rugby, but not soccer. So that's going to be 53 in the intersection between cricket and rugby, but those people don't watch soccer at all. And they say that 60 watch soccer and rugby, but not cricket. So 60 watch soccer and rugby, but they don't watch cricket at all. And then the last thing they tell you about the intersections is that X amount of people watch soccer and cricket, but not rugby. So that's going to go in the intersection between soccer and cricket. So as you see, I started with the intersection of all three. I then filled in the intersections of the two Venn diagrams, each of them with the intersection amounts that they gave me. So you will have a diagram that looks nice and neat like this one here. All right, you can see we've got all the intersections filled in, and we've got the number of people that do not watch any sports on the outside. How do we fill in these sections? What goes in here? Well, this is now where you go to the first bit of information that they gave you about each of the sports. They say in total 240 people watch soccer. So what's going to go in here? If 240 people watch soccer, then 240 minus the intersections with rugby, and then 78, the intersection with all three, and then minus the intersection with cricket will be the number of people who watch soccer only. So this little section here is the number of people that only watch soccer. They don't watch any other of the sports. So similarly for cricket, if you have a look, they say 180 people watch cricket. So if I want to know what's going to go in here, it's going to be 180 minus the intersections with the other sports. And those are the people who only watch cricket. Okay, so if we have a look at this, so we end up, after we do the subtraction, we get 102 minus x being the number of people that watch soccer only, 50 minus x, the number of people that watch cricket only, and then the number of people that watch rugby, because all of these intersections are actually known. So if you say, let's have a look at what the number of people was, 192 minus 52 minus 78 and minus 60, that gives me 2 people who only watch rugby. Okay, so let's just understand again what this diagram is showing me. The diagram shows me 3 things basically for each sport. It shows me what the intersection is with each of the other sports, or watching those other sports, if there are any intersections. In this case, there's intersections between all of them, so we can see that these events are not mutually exclusive. Okay, so it shows me the intersections. It shows me the number of people that only watch one sport, for example, that only watch soccer, only watch cricket, or only watch rugby. And it also tells me, this diagram, the number of people that don't watch any of these sports. Okay. So the question said, draw the Venn diagram and then find the value of x. So how do we do that? Well, I know that this entire blue section, which represents my sample space, must add up to 350. How do I know that? Because there were 350 people in this survey. So together, if you add all of the people who watch soccer, minus its intersection with the number of people who watch all 3 sports, and you add on the intersection with cricket, then you add on the number of people who watch cricket only, and then you add on the number of people who watch rugby only, and we add on the number of people who watch just the difference between, who watch nothing, sorry, we will get a total of 350. And I think let's put this into symbols so what I'm saying makes more sense. So if I take the number of people who watch soccer only, which is 102 minus x, I then add in the intersection with the number of people who watch both cricket and soccer, so that's x. And then I add the number of people who watch cricket only, which is 50 minus x. And I add 192, which is the number of people who watch rugby. And I add 38, that gives me the total sample space. But you might be looking at this and saying, but hang on, why are we adding the x to the 102 minus x plus x? I've only added it once. It also occurs in the cricket Venn diagram. So you can see that this x is in both for soccer and for cricket. Why am I not adding that value twice? Well, if you add that value twice, you will be double counting. Because remember, those people are repeated. They're watching both soccer and cricket. We cannot add them twice because we'll be over counting. Okay. So it's the same with all the intersections. I've included that intersection of 78, as you can see, 52, in fact, I think there was a little typing error somewhere there. So it was right in the beginning. It was actually 52 people that watch both cricket and rugby. So this should be a 52 there. And when I look at this diagram, I see that it's a 52 there. So if I include this rugby value with 192, I've included the intersection between cricket and rugby. I've included the intersection between all three and the intersection between soccer and rugby. Therefore, I cannot include that 60, 78, and 52 anywhere else. Okay, I hope you guys understand that. So therefore, I only have 192 here as the number of people for rugby. I do not include that those three intersections with the other two sports. All right. And we finally add the 38, which is the number of people that don't watch any of the sports. If I add all of these elements together, I should get 350, which is the total number of elements in the sample space. 102 plus 50 plus 192 plus 38 is 382. Minus x plus x, those cancel. So I'm just left with minus x is equal to 350. Take the 382 across. 350 minus 382 is negative 32. And then if I divide both sides by negative 1, I get that x is equal to 31. So therefore, the number of people who watch both soccer and cricket is 32. Guys, so it's so important to get this Venn diagram correct because any sub-question from here is going to be based on the Venn diagram. So if we ask you to find the probability of the number of people who watch, for example, soccer and cricket, it's going to be equal to 32 divided by 350. But it all starts with getting the correct numbers into that Venn diagram, and that starts with getting your intersections correct. All right, I think with all of that information, let's take a quick break. We're back after this. Hi guys, welcome back. Just before the break, we were looking at Venn diagrams, and now we're going to take a look at tree diagrams. Now, if you like magic, you're going to love the next question because it's all about the magic of tree diagrams. Let's take a look. So in this question, we are told that David is a street magician and he would like to draw aces one after the other from a deck of 52 playing cards. We are asked to draw a tree diagram to find the probability of various possibilities of drawing aces. Now remember, in a tree diagram, we have branches or arms as we call them, and we represent our outcomes on the tree diagram, and we represent the probabilities along the arms of the tree diagram. Now in this one, we've got to be quite smart with what we decide to let our event be. So I'm going to say, let the event of being an ace equal to A, and then the other event will be not getting 2, 3, 4, 5, 6, 7 all the way to a king and queen, but rather let's say there are two events. Either you're going to get an ace or you're not going to get an ace. Those are the two events that we are interested in. Okay, so let A be the event of drawing an ace, and let O be the event of getting any other card, okay, rather than listing each and every one of those events. Now, since we know that there are 4 aces in a deck of cards, the probability of getting an ace on the first draw will be 4 out of 52. There are 4 aces, and the total sample space is 52. You can simplify that if you want, or you can leave it as 4 over 52. So therefore, the probability of getting any other card, O, will be equal to, because it's the complement of getting an ace, it's going to be 1 minus 4 over 52, and that will be 48 over 52. All right, so let's represent that on a tree diagram. So we said, well, we can either get an ace or any other card, right? The probability of getting an ace on the first draw is the number of aces in the pack over the total number of elements in your sample space, which is 52. So we said the complement of getting an ace is getting any other card. So therefore, 1 minus 4 over 52 tells me that the probability of getting any other card is 48 over 52. Now, if we add across or vertically, we see that 4 over 52 plus 48 over 52 is equal to 1. Remember, the probability of getting an ace or any other card are mutually exclusive, and in this case, not only are they mutually exclusive, they are complementary. All right, now, if I've drawn, or if David has drawn an ace on the first draw, think about what's happening. So you had 52 cards in this deck of cards. But he has shown you one card and it happens to be an ace. So there's no longer 52 cards in this deck of cards. There's now going to be 51 because you've taken one out of the deck. Also, if it was an ace, there are no longer 4 aces left in your deck of cards. There's now 3 aces left in the deck of cards. So therefore, we would say these are dependent events. What happened the first draw will affect what happens on the second draw. So therefore, if he drew an ace out on the first draw, the probability of getting an ace on the second draw is going to be the number of aces that are left, which is 3, divided by the total number of cards left, which is 51. And that will give me, if we go along the arms of the tree diagram, this would give me the outcomes getting an ace on the first draw and then getting an ace on the second draw. So if I wanted to find the probability of getting an ace and then getting another ace, it's going to be equal to 4 out of 52 times by 3 over 51. And that will tell me the probability of getting 2 aces on 2 draws of cards. Okay, similarly, if we say 1 minus 3 over 51, that will tell me that there are 48 over 51 other cards that he could draw. So if we say I've already taken an ace out, that means I've only got 51 cards left to choose from. And then if we say, well, 51 minus 3, well, that will tell me how many other cards there are to choose from. So it's 48 over 51. All right, so that will give me the outcome, if we have a look at the tree diagram, of getting an ace the first time around and then any other card the second time around. So it's ace followed by any other card. So if I wanted to work out the probability of getting an ace and then any other card on this arm here, if we follow along on this outcome, it's going to be 4 over 52 times 48 over 51. When he's first drawing his cards, we said he can either get an ace or he could get any other card. So the probability the first time around of getting any other card we've already seen is 48 over 52. Once again, though, once he's taken out another card from the pack of cards, he still only has 51 cards to choose from. However, on the first draw, he didn't draw out an ace. So therefore, there are still 4 aces left in this deck of cards, right? So therefore, 4 over 51 will be the probability of getting an ace on the second draw if, so that's the second draw, if on the first draw he took out any other card besides an ace. Okay guys, so let's have a look at the questions now that we've seen how to work out the probability of each of those 2 outcomes. The last one, of course, would have been if we get 2 other cards on both draws. So the question we wanted to answer is we're going to use the tree diagram to see what is the probability that he draws 2 aces. Okay, so let's go back to our tree diagram. We're looking for the probability that he draws 2 aces. So to get the probability of 2 aces, that means I want an ace on both draws. It's simply going to be the probability of an ace on the first draw times the probability of an ace on the second draw. So 4 over 52 times by 3 over 51. And I'm going to leave it to you to multiply that out and get your answer. You can leave your answer in fractional form or in decimal form, or you can write it as a percentage. Okay, then the next question said, what is the probability that he draws no aces? So that will be the outcome where he gets any other card on the first draw and any other card on the second draw. So the probability of no aces is going to be equal to 48 over 52 times 47 over 51. All right, again, you can multiply that out with a calculator to see what answer you get and leave your answer in decimal, percentage, or fractional form. The third part wants to know the probability that he gets exactly one ace. So there are different ways that he can get one ace. He can either get an ace on the first draw and then any other card on the second draw, or he can get any other card on the first draw and an ace on the second draw. So we've got to add those two probabilities together. So what exactly are we adding? So here we're finding the probability of, the question said, exactly one ace. So the probability of one ace, so it's going to be the probability of an ace and any other card plus the probability of any other card and an ace. So that's going to then be 4 over 52 times 48 over 52, 48 over 51, sorry, because obviously our denominator will change because we've taken one card off the pack, plus 48 over 52 times by 4 over 51. Once again, you can add those together and work out the answer on your calculator. And then lastly, we wanted to know what is the probability of getting at least one ace. So at least one ace means you're going to either get two aces or you're going to get one ace plus one ace. So there are three outcomes here that we can add together. It's going to be the probability of getting an ace and an ace, plus the probability of an ace and then any other card, plus the probability of any other card first, and then an ace. And then you would add each of those together. So 4 over 52 times 3 over 51, plus 4 over 52 times 40, basically the answer you just found out in the previous question. And that will give you the probability of getting at least one ace. Now, another way you could think about that is to think about the complement of that event. So the probability of getting at least one ace will be 1 minus the probability of getting no aces. So since you've already found out the probability of getting no aces, we had to answer that question previously. And we saw that that was 48 over 52 times 47 over 51. So the probability of getting at least one ace will be 1 minus 48 over 52 times 47 over 51. So there's more than one way that we could answer that question. And that's important, is there's not always one single way to get to an answer in maths, but there are several correct ways to get to the same answer. Often, not all the times, but often it's the case where you can get to the same answer in several other correct ways. All right, guys, we have come to the end of today's section on practicing our questions. I hope that you join me the next time and send through any of the questions that you have to us so that we can answer them for you in the next session. Cheers.